Hello all, today we are going to attempt to simulate the dynamics of a magnetic dipole in presence of a uniform magnetic field. So the scenario is something like this. Consider a magnetic dipole lying in uniform magnetic field in upward direction. So here we have got our magnetic dipole represented by a magnetic dipole moment M and a uniform magnetic field in the upward direction. The angle between the M and B is theta. Okay, an example of a magnetic dipole would be a current carrying loop in which the magnetic moment would be defined as the current times the area vector according to the Latin rule. Okay, with that out of the way, let's see some facts about this system. So the two important facts about this system are that since magnetic field is uniform, net force on the dipole is zero. That is, there will be no translational motion. And the second important point is that since forces act on different locations on dipole, although net force is zero, there is finite torque about the axis perpendicular to both magnetic moment and the magnetic field and passing through the center of mass of dipole. That is, in this case, if we leave the magnetic moment at some angle theta initially with respect to the magnetic field vector, it is going to rotate about an axis passing through the screen, pointing away from the screen towards you. So for that rotational motion, the equation of motion is I theta double dot is equal to cross product of m cross b, where this I is the moment of inertia of the dipole and theta double dot is nothing but the second time derivative of this angle theta. That is, it is angular acceleration. And vector m is the dipole moment, magnetic dipole moment, and vector b is nothing but uniform magnetic field. In this case, as it can be seen from the figure, the right hand side reduces to mb sine theta. Moving forward, this ODE can be simplified to theta double dot is equal to mb by I sine theta. Now, our task becomes to solve this differential equation subject to some given initial conditions. That is, some given initial angular position and some given initial angular velocity. If we are given some initial positions, we can find out theta as a function of time. And once we have theta as a function of time, all we need to do is put the solution, which is theta as a function of time, into a graphics library and visualize it. So that is our goal. But the thing here is that this differential equation is nonlinear. It is not straightforward to solve using any traditional analytical methods that we have got. If it were, our job would be really easy. We would have just solved it analytically by hand and just send it to a graphics library to visualize it. It would be really computationally cheaper. But here, looks like we have to resort to some kind of numerical method to solve this nonlinear ordinary differential equation. This sine theta term is problematic on the right hand side. If we were considering small angle approximations, then we could approximate sine theta as theta for small angles. But since we are trying to attempt a complete simulation without any approximation, it would be wiser to resort to some kind of numerical method to solve above differential equation. So before we do that, also it is important to note an inherent assumption about this simulation we are going to do. It is as following, that the dipole is just a vector for us. We don't care about its physicality. Values of quantities like magnetic moment of dipole and moment of inertia of dipole are provided. We don't care about their computation. that is m and I are just given numbers. They'll be provided. You don't care that how to calculate them. Okay, moving forward, solving an ODE using numerical method. Okay, so the philosophy to solve an ODE using numerical method is summarized in following 3 steps. First thing we do is we discretize the time, which is the independent variable, into pieces of size h. So as you can see in the graph, we have uh, divided the time domain into pieces of size h. Now, second step is standing at xj, yj point. To approximate next point xj plus 1, yj plus 1, move along some sort of slope from xj to xj plus 1. That is, we are here at this point, and the goal is to find out the next point s distance away from this point. So we'll move along this orange slope and compute, that is approximate the value of y at xj plus 1 to be this value on the slope, which would be differing from the actual value by this amount. So that would be our error. Smaller the step size h is, the better the approximation. The third step is to repeat this over and over again, this step 1 and step 2, to get the whole curve, to get the approximation to whole curve. Once we have done that, we have basically solved the ordinary differential equation. So depending on what slope we use, we get different numerical methods with different accuracies, and this class of method is known in the business as Runge-Kutta methods. Okay, so in this video we are going to use Runge-Kutta method of order 4. What it is, we'll see next. Okay, so fourth order Runge-Kutta method to solve an ODE, d2y by dx square is equal to f of x comma y comma y1 is as following. These are the things, we'll see what they mean. Here the ODE is of this kind. The order is second order, and the right hand side is a function of independent variable x and the function y itself, and y1, which is the first derivative of y, that is this is dy by dx, subject to the given initial conditions. Y of x naught is equal to y naught, y1 of x naught is equal to y1 naught. These are the initial conditions. In our case, y naught would be in fact theta naught, which will be initial angular position, and y10 would be theta dot naught, which will be our initial angular velocity. Okay, so the iteration scheme of Runge-Kutta method of order 4 is given as following. If we are at point xj comma yj, and we have to find the value of the neighboring point xj plus 1 and xj plus 1 h distance away from xj, then iteration scheme is like this. The first derivative at j plus 1 will be y1j plus this some sort of weighted sum of k1, k2, k3, k4, where k1, k2, k3, k4 are nothing but the slopes in the neighborhood of point xj comma yj, as you can see from the expression, because f of x, y and y1 from the differential equation comes in, it is nothing but the second derivative. Okay, so it is k1, k2, k3, k4, these are the second derivatives in the neighborhood of the point xj comma yj. So with a little bit deeper look into it, you can really with the help of this diagram on the right, see what this k1, k2, k3, k4 means. For our purpose, we just need to use them as algorithm. So the iteration for the y will be yj plus 1 will be, that is this value is given by yj, which is this point, plus h times uh, first derivative at the current point, plus k1 plus k2 plus k3 divided by 6. So this is what we have got. So this is the recipe to solve the ODE. So next we move forward to solving the ODE using some code. One quick note before we begin to code: if we have magnetic field lying in upward direction and dipole lying in upward direction, for example, then if we nudge the dipole in this direction, and according to right hand rule, if you are using this coordinate system, this direction of angular displacement will be positive angular displacement, and if we nudge the dipole in this direction, then this will be, by right hand rule convention, negative theta direction. And our ordinary differential equation was theta double dot mb by I, and we had sine theta. So in fact, because if we displace it in this direction, the angular acceleration will be in the negative direction of angular displacement, so there will be a minus sign here. So there is a correction to what ODE we wrote earlier. Now we are going to simulate it using code. Now let's solve our ODE. We have got all the information on the right. We have to solve this ODE inside the box, and note that here we have got everything in terms of y and x, but in our problem we have theta and t. So keep it in your mind that when I'm talking about y and x, I'm really talking about theta and t. So we're going to utilize this Runge-Kutta scheme to solve our ODE. So first thing we do is we write out our constants. So we've got m, let's take it to be 1 for now. We've got b, let's take it to be 1 for now as well. We've got I, let's take it to be 1 for now. We can change it later. Next thing we have got is our initial conditions. So initial conditions we have is, first we have the initial time t0, let's take it to be 0. Then we have initial theta. Since there is no character theta on the keyboard, I'm representing the theta by capital T. So capital T naught, that is theta naught, initially let's write it out to be 0. We can change it later. And theta dot at time t is equal to 0 will be t1 0, and it will be 0. So we have got our constants, we have got our initial conditions. The next thing is to write the right hand side of our differential equation, which is a function of which is generally a function of theta t and theta dot. So we write right hand side function f of time t, theta and theta dot. In this case we have this as minus of mb by I times sine theta, which is here being represented by capital T. Okay, we have got that done. Now the next thing is to find theta at a time t. So what we are going to do is that say for example we are at xj and we have to find the value of the function xj plus 1 given the value of the function at xj and the first derivative of the function at xj. So utilizing this scheme we can find the value of the function at xj plus 1, and once we have that we can reapply the same iteration scheme at xj plus 1 and find the value of the function at xj plus 2, and so on. We can go on up to this time t and stop there. So the scheme is to move to time t in steps of h. So what we want is actually function theta of time t, and let's say the step size is h. This is what we want. First thing we need to know is how many number of iterations will be required to move from t not equal to 0 to t is equal to t. The number of iterations required are, say, capital N is equal to t minus t naught by the step size, which we are taking it to be h here. Once we have that, we need the placeholder variables for theta, theta dot, and t. So we take tj, initially it is t naught, then we take t1j, initially it is t1 naught, then we take tj, initially it is t naught. We have got this. Now next thing we have to do is we have to move all the way from j is equal to 1 to j is less than or equal to n. You have to move all the way from 1 to n, and this is what we need to do. Now we need to write out this Runge-Kutta scheme. To save some time, I'm gonna go ahead and copy and paste the scheme for you. So the scheme for our problem becomes this, and here where this is k1, you can verify from the picture on the right that what is written here is really correct, and this is k2, and this is k3, and this is k4, which are nothing but the slopes in the neighborhood of xj, and then we update our t to tj plus h, and then we update our theta by some weighted average of k1, k2, and k3, and the first derivative at the point xj, and then we update our first derivative as well. So now we have the information of the next point xj plus 1, and this thing is repeated over and over again n times until we get to t. So what we need is we need the value of time t at each of these grid points and the value of theta at each of these grid points. So we're going to maintain a list of it. So let's have a list here. Let's say time, initially we have tj, and let's also have another list. Let's call it theta values, that is t values, and initially it is tj. Now at every iteration, let's push these values of time and theta into that list. Now once this loop finishes, we'll have the list ready, and that will be our solution. So after this loop finishes, the solution we will we have to return tj, well, not tj, we have to return times, we have to return time list, and we have to return t values list, and let's put it in a list like this. So these things are done. Basically our solution is done. we have written our constants here, initial conditions here, then we have written right hand side of the ODE, then we have written time, the theta as a function of time here, and let's try solving it. Say for initial angular position minus pi by 2 and initial angular velocity 0. Let's see what the solution looks like. So the solution, say capital S, uh, let's say we want to evaluate up to t is equal to say 5 and in steps of 0.001. This is what we want. Then we will print it and see what the solution really is. So the solution comes out to be something like this. Well, let's see it here. So the time list is something like this: 0, 0.001, 0.002, and the corresponding theta values are these. So we have got theta as a function of time. The task of solving the ODE is complete. Next we move on to put this solution that we have got here into the graphics library. We are going to use P5.js for graphics. P5.js is a simple library used to create 2D animations. It's really handy to use. The basic structure of P5.js goes something like this. We've got a setup function and we've got a draw function. First, let's talk about setup function. Inside setup function, we put all the settings of our drawing. So we start out inside the setup function by creating the canvas. Your canvas is nothing but the space in which the drawing will be drawn. The next thing to put in the setup function is the stuff of first frame. What are we going to draw in first frame? So in first frame, let's start out by saying background. We take black background. Then next thing we do is let's move our origin to the middle of the canvas. So to W by 2 and H by 2. Okay, and then let's set the thickness of our brush. Next, let's set the color of our brush. Let's say it is orange, and let's now test whether it is working. So we draw an ellipse at the origin, basically a point at the origin, say of radius 10. Okay, so the library is working fine. Now the next thing we need to do is we have got this origin here, and the magnetic field is in the upward direction like this, and say the dipole is oriented with magnetic field like this, having an angle theta with it. So we want the coordinates of this tip. So we are using right hand coordinate system like this. So the coordinates of this tip with respect to this right hand coordinate system, this is x-axis, this is y-axis, are going to be we can see clearly from here that x is going to be your negative. Say the length of this dipole is L, length of this line from origin to this tip is L, then that will be L times sine theta Yes, and the y coordinate is going to be uh, the projection of this line on this magnetic field line. So y coordinate is going to be minus L. Well, not minus L. Y coordinate is going to be L times cosine of theta, like this. Now, these are the coordinates of this tip with respect to this right-handed coordinate system, which is what we have solved our ODE in. But the thing is that the computer graphics use left-handed coordinate system, which looks something like this. X-axis is in the same direction as the right-handed coordinate system, but the y-axis is inverted. So to convert the coordinates from right-handed system to left-handed system, we need to invert our y coordinate basically. So here we put a minus here. So now y is minus L cos theta. Now these coordinates we can supply to our graphics library and we'll be good to go. These are the coordinates of this tip with respect to this left-handed coordinate system. So let's do that. So we want a line from this origin all the way to the tip of the vector. So initially uh, first we extract the theta at t is equal to 0. So a solution was this s, which was a list, and the t values is at the second position. We extract out the first theta, and now let's draw a line from origin, that is 0 comma 0 to minus L times sine theta comma minus L times cosine theta. We need to define L, which is length. So let L is equal to say 100. So yes, we have got a line from the origin to the first value of theta, which is nothing but our initial value minus pi by 2. Indeed, it is minus pi by 2, since in this direction, as we have already discussed, it is the negative theta direction. Okay, that is done. Now this is just first frame. Things are still static. Now what we need to do is extract the other values of theta from this list that we have got, theta values list that we returned here. We need to extract other values of theta, and we need to update this value of theta in uniform interval of time. So that's what we do in draw function. Draw function runs again and again every few milliseconds or so, and each run of the draw function corresponds to one frame. So here what we need to do is everything will be same as in the first frame as far as the graphics go. So everything is same, but we now need to have something like some index here, I, and let's take initially I to be 0, and we need to increment it as soon as we enter the draw function, like this, by 1. So now you see this is starting to animate, right? What is happening is that every time the draw function is being run, the I is being incremented, and we are extracting the theta from the list of our solution, and then we are drawing the line from origin to uh, the tip at angle theta with the magnetic field. Okay, every time the draw function runs, I updates by 1 and theta value is extracted, and then it is affected in this line. The line is updated. So this is how it goes. So we are almost done. Theta, we are just drawing this line from origin to the value of theta as a function of time. Now, as you have seen, it has disappeared. The reason of that is that this list is finite, so there will be a time when I will exceed the length of the list. So here all the values of theta have been exhausted, so of course there is no next value of theta. So what we need to do to uh, let the animation continue running is to check if I reaches the length of the list, so we need to reset it like this and increment it by 1 only if I will be less than this value, which is the last index of the list as 1. So now the animation will keep on running, and we are done. Basically, we have solved the OT, and then we have uh, completed our task of visualizing theta as a function of time. Now we can do all sorts of stuff by changing the parameters that we have got. We can tweak the parameters and see how the behavior of the system changes. For example, if we increase the magnetic field by 100 times its current value, what will happen? Let's see. So increasing the magnetic field has increased the speed of oscillation, as we can see. If we increase it even further, the oscillation will be even faster. Faster the magnetic field, faster will be the oscillation. Now let's see what happens if we increase the magnetic moment. As we increase the magnetic moment, the dipole oscillates even faster, which is expected because the torque on the right hand side of our differential equation was m cross b. So if we increase any of m or b, the torque will increase, and thus the oscillation will be faster as a result of that. So it is good. Now let's bring it down to the normal values like this. Now let's ask what will happen if we give it some initial push. Before that, let's change the angular position to say plus pi by 2. So now start as plus pi by 2. Now if we give it some initial push, a high initial push than 1, then First it will be pushed in positive theta direction, as you can see. Then the effect of magnetic field will take over, and then it will perform the oscillations about theta is equal to 0, as you can see. If we increase the initial velocity even further, this is how the system behaves. Now if we increase the magnetic field, say at this point of time, all the dipole is pushed to plus theta direction in the beginning. Since magnetic field is very large, the effect of magnetic field takes over, as we can see. Okay, the next thing we do is we introduce some drag into the system. So if we model the drag as being proportional to the angular velocity, then uh, on the right hand side of the differential equation, the drag term will appear something like this. We'll have some drag coefficient, and we'll have a theta dot. Let's say drag coefficient is 5 to begin with. Now the way system is behaving is that it is the oscillation is dying down ultimately. No matter what the initial conditions, because of drag, there is torque in the opposite direction always. So that drag brings the system to the stable equilibrium position, which turns out to be theta is equal to 0. Now let's put the initial condition to be theta is equal to 0. And let's give it no push initially. If we start with theta is equal to 0 without any initial velocity, since the dipole and the magnetic field are aligned in the same direction, the torque is 0. Also there is no initial velocity, so the dipole remains where it is. There is no rotation at all. Now if we give some initial push, then of course it will oscillate about theta is equal to 0. And finally the oscillation will die down since we have got drag. If we had no drag, the oscillation won't die down, as we can see. This oscillation will indefinitely go on. If we decrease, if we increase the magnetic field, the oscillation will happen faster, like this. If we decrease the inertia even less, the oscillation will happen faster still. This way, we can model all sorts of possibilities. What will happen if there is no magnetic field at all? Let's see. If there is no magnetic field, this system is nothing but the case of a uniform rotation. There is no torque involved. We just give it some initial push, starting with some initial angular position. It goes on rotating with this angular velocity, and it behaves as a normal rotating object in presence of no external torque. Okay. Finally, let's try out a case, an arbitrary case, where we have very high magnetic field, very low inertia, and we start out at pi by 2, like this. See how it is oscillating very fast, and ultimately it settles with a stable equilibrium position. If we increase the magnetic dipole moment, the oscillation happens even faster, Finally, it will settle at the position of stable equilibrium, as we will see. It will take it more time this time, but ultimately it will settle. Yes. Now, if we make drag 50, say, and decrease magnetic moment, so it will settle like this. See, this is the case of quite stiff parameters. This way we can model all sorts of situations and see how the system behaves. We can even add more terms on the right hand side of the equation. We can add a forced torque external driver which will drive the system, and we can change the form of the drag torque, and we can do all sorts of stuff, right? So finally, I'll leave you with one caveat, and that is that although this system is being simulated, it is giving you the actual behavior, but the time scale involved is not the real time scale, since the time interval between frames is decided by this draw function, which is not equal to the time interval that we have used in our solution, which is in this case 1 millisecond, right? If we did a little bit more effort, we could make the time interval between frames equal to the time interval that we have actually used in solving our differential equation. So the gap between each theta value in this list is 1 millisecond in this case, but the theta is not being updated in 1 millisecond. It is decided by this draw function, which is uniform time interval, but not equal to the time interval that we are using. So the simulation is correct, but the time scale is different. It would be faster or slower in the real time world, the progression of time. Yes. So that's it. Try out all the possibilities yourself. I'll put the code somewhere online and put it in the description. You can go to the link and try yourself out. You can play with it. Okay, fine. Signing out. Thank you for watching.